In this video, we'll talk about slant asymptotes of rational functions. So we've mostly been looking at scenarios for rational functions where the degree in the numerator and the degree in the denominator are the same, or the degree of the polynomial in the numerator is less than the degree in the polynomial in the denominator. In this video, we're going to look at what happens when the degree of the polynomial in the numerator is greater than the degree of the polynomial in the denominator. So to get started, we'll take a quick look at what we've learned up to this point regarding asymptotes. We'll work through a problem where we have a rational function that has a slant asymptote, and then I'll give kind of a formal definition of slant asymptotes. So remember the definition of vertical and horizontal asymptotes. We would have a line x equals a for vertical asymptotes, which we find by factoring the polynomial in the denominator and finding all of its zeros, because we can't have a scenario where 0 is in the denominator, and that's when a vertical asymptote will appear. We use arrow notation to talk about the behavior around asymptotes. So we might say that as x approaches a from the positive side or from the right side, y might go to infinity. For horizontal asymptotes, the line y equals b is a horizontal asymptote if y approaches b as x approaches positive or negative infinity. So similarly, we might say that as x approaches infinity, y approaches b, and as x approaches negative infinity, y also approaches b. Now this, with horizontal asymptotes, it is okay for the graph of a rational function to cross a horizontal asymptote. It won't happen very frequently, but it can happen. To find asymptotes of rational functions, we look at whatever our rational function is with an arbitrarily complex polynomial in the numerator and another arbitrarily complex polynomial in the denominator. The vertical asymptotes, like I said, we get by factoring the denominator to find all the zeros. The horizontal asymptotes, if the degree of the polynomial in the numerator is less than m, then r, the rational function r, has a horizontal asymptote y equals 0. If the degree of the polynomial in the numerator and the degree of the polynomial in the denominator are the same, then the rational function has a horizontal asymptote y equals a sub n over b sub n, which is just leading coefficient of each of those polynomials. Now, if n is greater than m, we say that r has no horizontal asymptote. This is true, but it's only part of the picture. The punchline is that it doesn't have a horizontal asymptote, but it will have a slant asymptote. So let's do a little exploration now. So we will graph the rational function r of x equals x squared minus 4x minus 5 over x minus 3. So first, let's kind of take our typical analysis. We'll first find x-intercepts and y-intercepts, vertical asymptotes, etc., and then we'll conclude by looking at the slant asymptote. So remember, to find the x-intercept, we take the numerator and set it equal to 0. So we have x squared minus 4x minus 5 equals 0. This happens to factor to x plus 1 and x minus 5 equals 0. So we have x-intercepts negative 1, 0, and 5, 0. For the y-intercept, we plug in 0. So the y-intercept, we plug in 0 for x. So we have 0 squared minus 4 times 0 minus 5 over 0 minus 3, which gives us positive 5 thirds, and the coordinate pair 0, 5 thirds. For the vertical asymptote, obviously, looking at the denominator, the vertical asymptote will be x equals 3. And then if we look at the behavior near the vertical asymptote, we could find that y goes to infinity as x goes to 3 from the negative side, and y goes to negative infinity as x goes to 3 from the positive side. So let's put all this stuff on our graph, and then we'll talk about the slant asymptote. So we've got a vertical asymptote at x equals 3, right there. We have x-intercepts at negative 1, 0, and 5, 0. And we have a y-intercept at 0, 5 thirds, maybe right about there. And the behavior, we can kind of see from what's happening here, so that's okay. So I'll clear this out now. Now, in the past, when we're doing an analysis of a rational function, we've also used division, dividing the denominator into the numerator, to find transformations of that rational function in terms of the base function 1 over x. So let's do the same thing here. So we'll divide x minus 3 into x squared minus 4x minus 5. So the first question is, what do we need to multiply x minus 3 by to get x squared? Right, we're looking at the lead term in each one of those. So we need to multiply x minus 3 by x to get a leading term of x squared. We subtract x squared minus 3x. So that gives us negative x. Drop down the negative 5, so we have negative x minus 5. And then we need to multiply x by negative 1 to get negative x. So we subtract negative x plus 3. So we have a 0, and then a negative 8. So this is the interesting thing. In the past, we've typically ended up with a number there, but now we have essentially a line, right? So let's write this out. Now we know that we can rewrite r of x equals x minus 1 minus 8 over x minus 3. So just as when we've done this similar kind of analysis, this number, quote number, is the horizontal asymptote. It's still going to be the asymptote. We're just going to plot y equals x minus 1, and that will be our asymptote. So if we plot that here, x minus 1 looks like roughly like that. Now we just draw our function, or the graph of our function, into that asymptote. So we look like, and roughly like that. So you do see that when we get close to the asymptote, the vertical asymptote, x equals 3, if we're coming from the negative side, the left-hand side, it's going up to positive infinity. If we're coming from the positive side, the right-hand side, it's going down to negative infinity. Now, if I wanted to describe the behavior of our rational function around the slant asymptote, well, what's happening as x goes to negative infinity? Our function still goes to negative infinity, so y goes to negative infinity. And similarly, as x goes to positive infinity, y goes to positive infinity. So this is how you find a slant asymptote. So slant asymptotes, if r of x equals p of x over q of x is a rational function in which the degree in the numerator is greater than the degree of the denominator, we can use the division algorithm to express the function in the form r of x equals ax plus b plus r of x over q of x, where the degree of r is less than the degree of q, a does not equal 0, because then we wouldn't have a slant asymptote, and y equals ax plus b is a slant asymptote. In the next video, we will look at pulling all this together and kind of creating a process within which we can graph any rational function easily.